Hi everyone, Structural Analysis 2, Chapter 9, Force Method. Let's solve an indeterminate truss example in this review. So in this structure, we want to solve the problem and to determine the force in diagonal member of BD. So we do have a pin at A and a roller at B. So there is two reaction here. And if first of all we need to determine the degree of statically indeterminacy of this structure. So if we just jot down SI, statically indeterminate equation is member plus reaction minus 2 times J. Can easily see we have 6 member here plus 3 reactions, 2 for pin and 1 for RB, minus 2 times number of nodes, 1, 2, 3, 4 nodes, and it just simply gives us a 1 degree indeterminate. So if we just consider our a redundant reaction, like exactly if we cut BD through and we just consider the internal force of BD like a redundant and solve our problem like in determinate structure, then add the effect of redundant support and by superposition the original displacement of diagonal B should be 0 because there is no displacement for this vertical diagonal member. So in that case, if we just cut it through, it just gives us a 0 force member. As soon as we have this one like a 0 force member, and we can move to joint at D, you can easily see this one is 0, so there is just 2 members at D and a 12K at the direction of the member. So it just moves inside the horizontal member and it just gives us there is no way to distribute this horizontal force to the vertical component. This is 0. So all of the force goes to like a compressive force. It pushes the pin, it pushes the member as well, and this part DA is a 0 force member. Like the other one, if this one is 0, reaction at B is also there is no horizontal one. If this is 0, it's just all the way of RB. Whatever RB is just going to this member and make this one the horizontal likewise like 0. So we have a three of our members are our 0 force members and we need to solve the internal forces for the rest. So compatibility equation, it just says don't solve the problem for delta 1 of P, which is the real forces plus delta 1 with redundant reaction and the summation of them to principle of superposition should be equal to the total movement, which is there is no motion, just gives us 0. So if we create a moment about, for example, point A, it just gives us by times a distance of 3 meters is equal to 12 minus 12 kilonewtons times 4 equal to 0, and it just simply gives us by is equal to 16 kilonewtons. As soon as we have that one, we can jump to joint B at here. So if we have a upward push to the joint, it just push the member as well. So it just gives us a member BC is a negative compression of the same amount of reaction and compression. So that's our member force. And if you look at joint C, this is joint C, and there is a negative 12. It just says negative is push to the joint. So there is a push, there is a push. If we just want to calculate the internal force at AC member diagonal AC, it just gives us a rise over run 3 over 4 summation of force in x goes 0. It just gives us a negative because this is in negative x direction, this is positive x direction, and 3 of 5% of NAC plus 12 goes 0. There is no other force in x direction. It just gives us NAC is positive 20, and positive, it's consistent with our arbitrary direction. So if that's the case, if you look at the joint C, NAC is pulling the joint, so it should pull the member as well. So this is a 20, positive 20. That's a tensile force in diagonal AC. Now we have the forces for all the members. So we have this one, this one, this one. Other are zero force members. So as soon as we have that, we can replace the numeric value of each member of the structure on it and just move on. And now remove all the forces and then apply apply 1 Newton at each part of the dissected diagonal B. So in that case, if you observe joint D, there is a downward push with the amount of pull, the amount of 1 unit, and these are the member N internal small n inside the C. This is a virtual work method, virtual moments, virtual axial force, and NDA, which is this part. And if you develop the summation of force, for example, in x direction, it just says a 3 over 5 of positive 1. Again, this is positive, plus NDC goes to 0 in x direction. This is positive x, and it just gives us NDC is a negative, and that negative, it just says it's not pull but push. So NDC should be, if it's push the member, if it's push the joint at the same force applied to the structure, and that's a compression, and with the value of negative 0.6, so that's a negative 0.6. And at the same time, if you summation of forces in y direction goes 0, summation of forces in y goes 0, it just gives us a negative, the NDA is a negative 0.n, and it just gives us the internal force in member AD. If you just move to joint B, the same amount of 1 unit force is just pulling upward the joint at B, and we do have NBC and NAB. Summation of forces again, it just gives us NAB is equal to 0.6, and that's NBA, so that's a push, and it just comes to be positive. That's consistent, and push the joint to the joint is a compression, that's negative here. As soon as you have it like here, you can go to the last a joint like C here, and you have NAC with these two other forces, and it just gives you internal force of AC is equal to positive 1. If it pulls out the joint like what you can see in the figure, and then it just consistent to be equal to that one is positive, it just verifies that's a pull. The joint at C, it should pull this member, so that's a positive 1. As soon as you have that one, we can write all the internal forces on a structure, the usual axial force, and 1 times delta 1 P is equal to summation of small and capital N times the length. That's the virtual work method approach. So original N, small n, and as soon as you multiply each, for example, points, this part 0.6 times point negative 12 times the length of member, which is 3 meters, plus negative 8 times negative 16 over EI times the length, which is 4 meters, and plus a 1 times positive 20 EI times the length, which is, if this is 3, this is 4, this is 5. If you add them up together, it just gives you delta 1 is equal to positive 172.8 E over 8. And we are halfway through for our structure, so we need to go to other part. Now the effect of the redundant reaction, 1 times delta 1 of reaction is equal to small n capital N over EA times the length. So this time, if we already calculate the effect of small n, if you simply multiply all the members with just a reaction. So that's a negative 0.8 times R, negative 0.8 times R, negative 0.6 times R, 1 times R, and negative, just simply multiply all them by R. It just gives you capital N for this part. So small n, again capital N, and it just, if you get the redundant reaction, because we are looking for this part, and that's summation of n squared over EA times L. If you do so, it just gives us, we have, my bad, we have two members like point negative 6 times point negative 6 R. We already take out R or R1, they are the same, and it just point negative 0.6 in parentheses squared, and we have one of them at the top, one of them at the bottom, so that's two of them. Then 2 negative 0.8 times negative 0.8 times R, again the factor of the redundant reaction times the length of the member, which is 4, plus then two of these diagonal 1 and 1, as you can see here, times 1 times 5. The length of diagonal is 5 meters. And if you do the math, this part, it just gives you the internal energy for all 6 members. Internal energy for all 6 members. And it just gives you R1 out of the summation or integration n squared L over EA in terms of the parametric. And we call that a flexibility coefficient and show that by F11. So again, if we call this flexibility coefficient, if you want to know how that means, if you have a spring with the stiffness of K, stiffness of K, stiffness of K, if you apply a force of F, it just moves down by the amount of delta. You can easily see the delta of a spring is force over K, and if you rearrange the equation, 1 over K times F, we call 1 over K the flexibility. K is a stiffness, and 1 over K, which is F, is flexibility. In fact, F, or 1 over K, is a measure of displacement per unit force, and you can easily see the unit of that is the force. So we can almost call that this is in the sense of force. That's why we call chapter 9 the force method, the determinate or indeterminate structure with the force method, because that's in the nature of the force. And then let's jump to the rest of the problem. Now we have delta 1 due to real force, delta 1 due to redundant reaction, and the diagonal BD doesn't move, so there's no displacement for it. It's equal to 0. That's the mathematical equation. And it just says 172.8 over EI plus 17.28 over EI times reaction or redundant reaction at equal to 0. It just simply gives you R1 is equal to negative 10. It just simply says internal R1 redundant is internal force of diagonal BD is at compression and with the numeric value of 10. So that's how we can get the redundant reaction, and as soon as you have that one, you have all the problems solved because we were looking at the redundant reaction. That's the solution of solving indeterminate truss by the use of the force method based off virtual work. Thank you. We'll solve more problem, terminate problem in trusses. Thank you.